Let's talk about the energies and forces involved in electron-nuclear interactions. By analogy, we'll start first with a gravitational mass attracted to the Earth. Here's an astronaut. That person is attracted to the Earth through the force of gravity, and that's given by the gravitational law that Newton came up with. And it's equal to some constant times the mass of object 1, the Earth, mass of object 2, the astronaut, over the distance between the two squared. Obviously, when the astronaut is on the surface of the Earth, it has lower energy. You have to put a lot of energy in to go against the force of gravity to raise the astronaut so it's in space, and then it's no longer attracted to the planet. So again, there's a relationship between energy and force, and the gravitational force is what applies when we're talking about two massive objects. Now let's extend the analogy to the nucleus. For instance, here's a calcium, has 20 protons, mass number of 40. This is the electronic configuration: 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. We talked about an energy diagram, electronic energy diagram, in which the 1s electrons are closer to the nucleus, hence they're lower in energy, just like an astronaut closer to the Earth is lower in energy. And then these orbitals, as we're going in this direction, have higher and higher energy. And they're further and further away from the nucleus. These orbitals have more and more nodes as well. So if I want to take an electron from, let's say, 1s orbital, so it's strip it away from the atom, that would take a lot of energy. It would take a lot less energy to remove the outer shell electron, indicated by this little red electron, out, so it's no longer connected to the atom. And that's because the electrons are attracted to the nucleus, not through gravitational force, but something called the Coulombic force. And it's equal to a constant times the charge on one object, in this case the nucleus, charge to the charge on the electron over their distance squared. It's a very analogous law. We know atoms are reactive. The noble gases aren't, but they either try to seek, gain an electron or lose an electron to achieve a stable outer shell. Let's look again at calcium with the 4s2 electron. To get stable, it would remove the last two electrons. These are the highest energy electrons. And if we remove both of those, it would essentially become calcium 2+. Just removing one, it would be calcium 1+. The energy required to remove the highest energy electron, which obviously would be the valence electron, is indicated by this arrow. At this point up here, the electron is no longer connected to the atom, and we can say that the energy is ionized. And again, Coulombic interaction is the force of attraction that attracts the electron to the nucleus. And obviously, the further electron is away from the nucleus, the higher its energy. You have to put less energy in to strip it away and make it an ion. The energy required to remove the outermost electron, highest energy electron, is called the first ionization energy. Now, what kind of positive pull does that electron feel when it's an outer shell electron? Well, if we can think about it, here's 20 positive neutrons in the nucleus, but there's all these intervening inner shell electrons that are present. So in a way, these inner shell electrons would shield this outer shell electron, 4s electron in calcium, from the nucleus. So it would take, again, less energy to remove this outer shell electron. We can sort of quantify that a little bit by talking about the core charge, or the Z effective. And that is the effective positive charge that an outer shell electron feels. And again, it wouldn't feel plus 20 because there's these electrons here, which are effectively 18 inner shell electrons. The core charge, or Z effective, is the number of protons in the nucleus that could be attracting this outer shell electron, minus the number of inner shell electrons, and in this case 18. So we call the core charge, or Z effective, is 20 minus 18, which is 2. And calcium is in group 2. It actually equals the group number. Core charge is an incredibly important concept in determining the periodicity of atoms in terms of their properties.